to introduce the expert. I am pleased to introduce our distinguished resource person for today's session of the Faculty Development Program. We are fortunate to have with us Dr. N. Vijayan Sir from National Physics Laboratory, New Delhi, who brings with them an extensive background in the growth of technologically important single crystals. Dr. Vijayan Sir received a PhD in Material Science from Anna University, Chennai in the year of 2005. His current research is growth of nonlinear and piezoelectric single crystals by the vertical Bridgman technique and solution growth techniques, and preparation of Indian reference material for the calibration of sophisticated instrument which is coming under Bharatiya Nirdesh Dravya scheme BNTs. He has published more than 300 publications in reputed journals with good impact factors. Also, Sir is having citation around 6,500 plus. I-10 index is 167. He has received many awards such as Young Achiever Award, Outstanding Performance Award, Best Innovative Researcher Award, Bharat Excellence Award for Outstanding Contribution to Material Science. He has successfully completed many research projects over 32,000 32 crores in funding from various agencies like CSAR and DST. Now I hand over the session to Dr. Vijayan sir.
Vijayan sir is known to many of the people across the India, and I want to make a point that maybe myself and Vijayan sir interacted or started to know each other nearly about 15 years back when I went to CSR lab for a meeting or interview, I think so. Till now, he is always an ever enthusiastic person, and he never misses to amaze with his excellent speech. So it was my great pleasure to invite my friend and my well-wisher. Whatever thing that I tell, it is right. So with this word, I hand over the session to Vijayan sir. Sir, welcome you, sir. Thank you very much.
Good evening to everyone. So first of all, I have to thank my friend and then my well-wisher, Dr. Adi Mulam sir, for his always encouraging us and also given the chance in the ATAL program. Almost it is going to be another few days. And also I'm thankful to the police chair. So anyway, previous session also we have seen by Professor Sivadana Pillai sir. He is extraordinary personality. In this age also, what are all the expressions, what are all the explanations he has given, it is really amazing. So we have to thank them always, and then they done really a wonderful job. So can we go to my session? So today they have given the chance to me to discuss about the advances in optoelectronic materials. So my topic, I have chosen that mastering the growth of defect-free single crystals for cutting-edge applications. Why I have chosen this title? Anyway, proudly I can able to say that I am a crystal grower. And one thing we have to make an important note that we are having almost more than 150 to 160 crores of Indians. But really very sad to say that there is no crystal growth industry across India. But we are using many of the crystals related applications in our daily life for our technological applications, for our electronic industries, even our solar cell applications, mainly based on silicon single crystals. We are always importing the silicon wafers from the other nations. So that's what Government of India, they have initiated the mission that Vikshit Bharat. We got the independence in 1947. At least from 1947 to 2047, 100 years, we can be self-reliance. So that is my plan, and then that is my today's essence of my talk. So we have to travel towards Vikshit Bharat. So please join with me. So today is 28th January 2025. It is really excellent day. Today is Tuesday, and exactly after 1 month, 28th February 2025, we are going to celebrate. I am audible, sir?
Sir, you are audible, sir. It's very clear.
Yeah, fine.
Ah.
Exactly after 1 month, we are going to celebrate the National Science Day. I hope all the professors or many of the research students from various places across the country, you are attending today's event through online. After 1 month, we are going to celebrate the National Science Day. Everyone knows that Sir C.V. Raman, the great personality, the great visionary, he discovered the Raman effect in India. Always I used to insist in all platforms. Sir C.V. Raman is an Indian. He got the Nobel Prize in 1930. He discovered the Raman effect in 1928. After 2 years, he got the Nobel Prize. We are all very proud. But one thing we have to make an important note, that even we are having 150 to 160 crores of Indians, almost we are going to pass 100 years. We are not able to make the even Raman's discovery, that Raman spectrometer. Raman is an Indian. Raman discovered the Raman effect in India. But Raman spectrometer we are purchasing from Germany. Raman spectrometer we are purchasing from Japan. So this scenario we have to change. That's what Government of India, not only for this mission, in almost all the sectors of our R&Ds, we have to be self-reliance. You can take the space technology, whatever the previous session speaker, he has clearly mentioned that we have to be a self-reliance. Even you can take the example of cryogenic. You can take the example of in any of the sectors in our daily R&D, even automobile industries. I can able to say that almost all Indian roads are filled with foreign cars. Even if you go and then see in our house, what are all the sophisticated gadgets we are using in our daily life, everything made in some other country. Even we are having this much population and less than 40 years of age, approximately more than 45 to 50 crores. It is equivalent to almost 5 times of Japan. One person asked me, we are always saying that India is the developing nation from the past 77, 78 years. The nations, they got the independence similar to during 1940s. They already became the developed nation. What is the difference between the developed nation and the developing nation? Developing nation and then developed nations both are having this similar human resources. Even we are in a better position. Then what is the difference? Why we are calling as the India as the developing nation? One thing we have to make an important note, because you are all academic personalities, you are managing the students, you are generating the human resources. That is really excellent. We have to always salute you. But one thing we have to make an important note, that what are all the knowledge we are generating, what are all the knowledge we are gaining through our system, it is only in the library level. What are all the knowledge they are gaining from the other nations or the developed nations, what we can call. So their knowledge they are generating, and they are converting their knowledge into products. They are converting their knowledge into devices. They are converting their knowledge into technology transfers. But in our case, if you take, for example, I am a PhD student, or in case if I am a MTech or ME student, at the final year, after maybe everyone knows that almost 5th year of our PhD, we have to submit almost binded volume of 250 pages. Or MTech, in case if I am MTech student, almost 50 to 100 pages, I have to submit my thesis report. After my viva's examination, what are all the inventions, what are all the technology, what are all the new devices proposed in my thesis, that is not implemented, that is not come out as a product. It is only in the thesis form. It is only in the hard bounded volume form. It is displayed in the library. My next juniors, they are coming.
Online class.
Sorry, sir, some disturbance.
Yeah.
Please proceed.
So, yeah, in case if you see, my juniors, they are coming, they are going to library, and then they are seeing my thesis report. They are doing some delta X additions. Again, they are making as the thesis form. Again, they are displaying in the library, whether it is in the thesis form or if it is in the journal form. So our knowledge, we are not transforming beyond the library level. But the countries we are calling as the developed nations, they are also gaining the knowledge in the academic system, but those knowledges they are converting into technology, they are converting into devices, they are converting into technology. So these things are missing. So everyone has to work very hard, and we can join our hands together. Definitely before 2047, we can make our India self-reliance. So that is the main motive of this. So National Physical Laboratory, I hope many of the attendees, I have seen the names. I hope everyone knows about the National Physical Laboratory. The other name is National Measurement Institute of India. I hope many of the professors or maybe the students, you know about the IST, Indian Standard Time. Whenever you are sending email or receiving email, or whenever you are using your online transactions, or whenever you are using your debit or credit cards, you can able to see the IST. IST, Indian Standard Time, is maintained by National Physical Laboratory through CCM atomic clock. The National Measurement Institute of India status was given by our Indian Parliament. It is simple. Everyone knows about the SI units. 7 base SI units are there. During our school days or maybe college days, we have clearly seen, or maybe we read and then we forgotten about the 7 base SI units. Now I am asking you, you can recall all the 7 basic SI units and just you can correlate in your daily life. I am saying without the 7 base SI units, it is very difficult to imagine a single second in our life. Whenever you are waking up in the morning, till whenever you are going to bed, without the 7 basic SI units, it is very difficult to imagine our daily life. All the 7 basic SI units, primary standards, are maintained by National Physical Laboratory. It is coming under CSIR, Council of Scientific and Industrial Research. CSIR is the major R&D body, that is Research and Development Organization. Under CSIR, we are having almost 38 laboratories all over India. Each and every state, at least 1 or 2 CSIR laboratories. All the CSIR laboratories, they are working, or the researchers, they are focusing for the development of societal based products. So this is the brief introduction about the National Physical Laboratory. Maybe in the future, if you are having the time or if you are having the chance to visit Delhi, you can always come and then you can see the beauty of National Physical Laboratory. Not only that, you can able to see what all the research work NPL is doing for the benefit of our nation. And sometimes whenever I am explaining National Measurement Institute of India, you may be getting confusion, or you may be correlating this to some other. Just for brief information, this is called the National Metrology Institute of India. National Measurement Institute or National Metrology Institute, both are same. What is metrology? Metrology is the science of measurement. What is the science of measurement? We are doing measurement. We are having, meter scale, and then through that I am taking my shirt size approximately 1.5 meter, or maybe my pant size. So that measurement is totally different. In case if you are measuring about your scientific characterization results in the scale of nano level, how you can measure it? Normally we have to see the precision. That high precision and then high accuracy is always playing an important role in our day-to-day research life also. So that's what National Metrology Institute comes into the picture. Metrology is the science of measurement. You can see nowadays, we are struggling to publish in a few impact factor journals. Those days, the giants of National Physical Laboratory, they continuously published the role of National Physical Laboratory in nature. Not only that, the first founding director of National Physical Laboratory was the student of Sir C.V. Raman. His name is Dr. K.S. Krishnan. Because of his contribution, because of his dedication into scientific era, where the National Physical Laboratory is located, that street name is called the Dr. K.S. Krishnan Road. You can imagine. So that's what we used to say, that the nation always remember whenever we are working for the nation. So Raman effect, everyone knows. 1928, he discovered the Raman effect, and he got the Nobel Prize in 1930. So almost through the Raman effect, he published almost 10 papers. Simplest equipment. The cost is less than 500 rupees. Through this, we can able to learn many things. For doing research, it is not necessary to go for crores of rupees. Through that, we can also know that after 1930, 2030 is going to come after 5 years. We never ever tried for the Nobel Prize from our Indian soil. Simplest equipment, simplest design, but one sad part is he designed the equipment in India. Still, it is there in the IACS Kolkata, Indian Association of Cultivation of Science Kolkata. But the sad part is the present scenario is we are taking Raman spectrometer from Germany or Japan. If you compare the total population of those countries, it is less than 10 crores. These things we have to keep in mind. That's what I used to say, that at least it is not necessary to go or beg the other nation's technology. We can make our own technology, because if you see our Indian geographical region from Kashmir to Kanyakumari, we are having varieties of geographical conditions. Kashmir, it is too much cold, or if you see the Maharashtra, some of the places it is too hot. Southern part we are having humid weather. So the technology, whatever we are getting from the other nations, how it will survive. So our Honorable Prime Minister always insisting that now present scenario is we are all simply importers. Our Prime Minister is encouraging that from importing level into exporting level, whenever we are reaching, then definitely India will become the developed nation. You can see the members, they worked along with the Sir C.V. Raman. In the center, you can see Dr. K.S. Krishnan. He belongs to a small village close to Srivilliputtur. That name is called the Vattirayiruppu. And he came from that place and he joined with the Sir C.V. Raman sir. And then, extraordinary work they have done. And then they have published the series of nature papers. And then he reached the level of the first founding director of National Physical Laboratory. The inauguration of National Physical Laboratory happened 4th January 1947, before our independence. And officially it was inaugurated from 1950 onwards. During the inauguration session, our former Prime Minister of India, the then late Prime Minister, Pandit Jawaharlal Nehru, he was mentioning that instead of becoming a Prime Minister of India, in case if I will get the chance to become the director of the National Physical Laboratory, that is the greatest honor for me. So that is the simple sentence he has mentioned. And you have to note a very important note. We are having almost more than 150 crores of population, and always we are depending many nations for all the technologies. Even our solar cells, now Government of India, they are encouraging, that is called the solar missions. But always we are importing from the other nations. So what are all the drawback from this? In some other nations, the same silicon solar panel, it is surviving for more than 25 or 20 years. But in many of our places, the silicon solar panels are surviving for maximum 5 to 10 years. See, what are all the drawbacks? See, what will happen? Instead of, in case if it is surviving for the whole life, approximately 25 years, instead of that, 50% of the life, in case if it is surviving, then finally we are removing the panel and then we are throwing. So indirectly, we are making our India as the dump yard. Now, in case if we are making our own silicon technology, our own single crystals technology in various sectors, various applications, various technology like a piezoelectric, photoelectric effect, electro-optic, optoelectronic modulators, frequency doublers. In case if we are making our own technology, we can able to make a very good single crystals, and we can play and we can able to rule the electronic industries. Taiwan, the total population is approximately 1.5 to 2 crores. They are ruling the world of integrated circuits. Integrated circuits mainly they are making from the silicon single crystals. So these things we have to keep in mind, and then we have to start working on the development of various single crystals. For that, mainly we are using two major techniques. One is growth from solution, another one is growth from melt. Growth from melt itself, it is having the explanation. We can able to melt the material and then we can able to grow the single crystals, because why I am telling single crystal growth is an art. Everybody can grow the single crystals, but growing a defect-free single crystal is the excellent technology. Directly you can able to make those single crystals for device fabrications. But how to minimize the defects? Because ideally growing perfect single crystal, it is impossible. It is very difficult. But at the same time, we can able to grow the very good quality single crystals by minimizing the defects. So what are all the defects? What are all the defect formation during the single crystals? So whenever I am talking about the single crystals, the non-single crystal researchers may be knowing that. So what are all the applications are there? Even it is starting from your house in the early morning, whenever you are waking up, and then whenever you are firing your gas stove, you are using the gas lighter. That is the concept of piezoelectric single crystal. Even your wrist watch, whatever the brand, Timex or Titan, whatever the brand, you can see in the bottom quartz. Quartz is the excellent piezoelectric single crystal. Now the fossil fuel, what are all the nature it has given, how many years it will come? It will come for another maybe 10, 20, 30, maybe you can keep it for another 50 years. After that fossil fuel, it is very difficult to depend. So we have to make our own generation of electricity. Piezoelectric single crystals, through that we can able to generate the electricity. Even silicon single crystals, you can able to convert sunlight into electricity. That's what I used to say, that nature has given free of cost water. Nature has given free of cost oxygen. Nature has given free of cost energy. But how many people we are using the free of cost energy? So if we talk about the single crystals, we can able to say n number of applications used in quartz watches, frequency conversion devices, even your India glazers, YAG, yttrium aluminum garnet is an excellent melt-grown single crystal doped with neodymium. That we can use it for the laser cutting tools. Artificial diamonds. Natural diamonds are very expensive. We can able to make the artificial diamonds in the laboratory. That is the excellent business. Now in Delhi, earlier one former scientist of National Physical Laboratory, he started his own industry and he started making the artificial diamonds, and he started exporting the artificial diamonds to other nations. In the field of solar cells, light emitting diodes, like that we can say n number of applications for the growth of single crystals. But one thing we have to keep in mind, that these single crystals, whenever it is in the perfect form, that is defect-free form, we can able to use it for the directly the device fabrications. In case if the single crystals are having the defects, what we can do, how to minimize, how to avoid the defects, these things we are going to discuss one by one. I have taken few examples. Benzimidazole, it is one of the excellent material. It is the organic material C7H6N2, its molecular formula, and we can able to grow the single crystal by slow evaporation solution growth technique. Even maybe I forgotten to show that slide. Sir C.V. Raman, he was handling and he was carrying excellent solution grown ammonium dihydrogen phosphate single crystal that was having excellent piezoelectric applications. Like that, even the method or the material, irrespective of that, we have to see the applications. Benzimidazole is having excellent nonlinear optical behavior. We can able to compare this with the standard potassium dihydrogen phosphate single crystal, and potassium dihydrogen phosphate single crystal is showing one time of nonlinear optical efficiency. It is showing approximately 3.5 times more than that of potassium dihydrogen phosphate nonlinear optical efficiency. These single crystals, why I have chosen? I have grown this single crystal by 3 different techniques. See, now you can see this is the maximum size one can able to grow by slow evaporation solution growth technique. You can see, in addition to that, you can able to see different facets. Different facets are having the different directions. Each and every direction, it will show different property of nonlinear optical efficiency or different values of nonlinear optical efficiency. So I will come later how I have grown the same crystal with a single direction and how I can made it as a very big size single crystal of benzimidazole by melt growth technique. Maybe in the later slide, maybe I will explain you. I am a crystal grower. My main aim is to search, to examine variety of single crystals, and in that I have to find out which is the best nonlinear optical single crystal or which is the best piezoelectric single crystal. In case if I am finding those material, then my next job is to grow defect-free single crystal. Now, another technique we have, these are all the designs. One thing we have to make an important note as a crystal grower or as a nanomaterial researcher or as a carbon nanotube researcher. One thing we have to make an important note that I have to design my own equipment. I have to at least make some other new designs in my research. So we developed our own seed rotation technique, seed platform we made it, and we have put one small seed crystal, and that crystal, the same similar solution of saturated solution we pour, and finally, because of the bidirectional, clockwise as well as the anti-clockwise, the concentration making throughout the solution is uniform, then I can able to grow very good quality single crystals. These single crystals, if you compare with the market rate, 5 mm by 5 mm, outside they are selling approximately few $100s. This is some of the organic single crystals and then semi-metal organic single crystals. But we can able to grow with very less expensive equipments of slow evaporation or seed rotation technique. And another one, our own Indian researchers, Professor Ramasamy sir and then Shankar Narayanan sir has developed the new technique that is called the unidirectional. You have seen our earlier single crystal of benzimidazole. It is having different directions, different facets. Different facets are having different directions. Each and every direction it will show different nonlinear optical value. But after knowing its phase matching direction, then I can able to grow the particular direction as a whole material. What are all the advantages for this? In case I can able to grow a bulk size single crystal, the whole single crystal I can able to use it for the device fabrications. In case if the same crystal, if I am growing through this normal slow evaporation solution growth, some direction is having highest efficiency, the remaining portion I have to cut and then I have to throw. So this liquid solid efficiency or conversion ratio is more in comparison with the normal slow evaporation solution growth. The simplest ampules or crucible or the container, we can able to design our own. This was the initial setup, and after that many designs, because the researcher we have to find out the new ways, we have to find out the new technology, we have to find out the new methodology for improving the already existing one. This is the old one, again we improved for, if you pour some highly concentrated material, then what will happen? Slow evaporation. After that again you have to pour concentrated solution. In case if both the concentration differs, then it may affect the single crystal growth. How to avoid? These things also we have clearly reported in many of our literatures. Some of the designs we made our own, and you can able to see the crystals of benzimidazole, it is following the same growth pattern of the direction of approximately 101 or something like that. We can able to see the very good quality single crystal. So these are all the organic materials. Approximately, see because we are using the dimethyl formamide as the solvent, after a particular period, then we can take the single crystal and then you can cut and then you can polish and then you can make it as a different wafers for your applications. So these single crystals we have grown by slow evaporation solution growth. Another thing, in our laboratory we are having the melt growth, because melt growth, it contains two different techniques. One is vertical bridgement, that is bridgement technique. Another one is the Zukralski technique. Almost all over the world, daily they are growing silicon single crystals, approximately thousands of tons for our regular applications of silicon solar cells or integrated circuits or n number of applications. Even if you go and then ask some of the thin film researchers, what are all the substrates they are using, they can able to say that I am using silicon substrate, or they may be saying that I am using some optical materials, single crystal substrates. So single crystals are useful for varieties of applications. Even the researchers, they can use these single crystals as the wafers or the substrates. So this is the small setup we have procured from RBK Crystal Technology, that is again Indian. And we made our own furnace, because whenever I am a crystal grower, whenever I know that what is the condition for the crystal growth, then I can able to wind my own furnace. I wounded the furnace. Then in that, how many profiles, temperature profiles I can able to make, how many zones I can able to make, everything I know that. Based on that, we made a transparent furnace and then attached with the translation system. So now my furnace and then my translation setup is ready. But now here, I have to apply my research mind. Whenever I am using the crucibles, whenever I am using the containers for the growth of single crystals by vertical bridgman, so again I have to understand the basics of bridgman and then basics of the crucible designs. So 3 designs mainly we are using. And in case if I am making the V shape, the conical bottom or the tapered tips, how it can increases the concave solid liquid interface or flat solid liquid interface or convex solid liquid interface. So in case after the growth, if I am finding out my crystal grown, that means first of all powder material I have taken, then my material is going to molten state. Then after that it is in this solidification form. So it is crossing from your solid, liquid, then solid. So whenever it is in the final form of solid, it should be at least in the flat surface. If it is in the flat surface, then your defects are very, very less. In case by controlling the temperature profiles, temperature gradients, if I will get the convex solid liquid interface, then my crystal quality is really extraordinary. The defects are very meager. But at the same time, if I am a new crystal grower or I can't able to judge my temperature profile throughout the furnace, then chances are there for getting concave solid liquid interface. In that case, definitely your crystals are bound to form many of the defects. That is the grain boundaries or maybe the surface defects. Lot of defects will form. So this is the very, very important for all the single crystal growers. In case if I will come to know these things, then I can able to play. I have taken one organic material, transparent furnace I have taken, everything we made our own. So finally I filled the material. I underwent for the high dynamic vacuum of 10 power minus 6 star. Then I translated my ampule. Ampule is the container. Ampule is the container. Then slowly it is going inside the furnace. I can able to see inside what is happening. In some of the cases, they are using the ceramic tube. So ceramic tube, some advantages are there, some disadvantages are there. But here you can able to directly see what is going inside. So here I translated my ampule, and then at the center of the furnace, it got melted. Then finally it is going down. It is going down. Then my whole liquid form, it is slowly converting into a solid form. So I can able to play with the translation speed, 1 mm per hour. Translation means from one place to another place, it will take at least 1 hour for translating 1 mm. Even I can able to reduce it to 0.5 mm, depending upon the material, because there is no constant value here we should not keep. Depending upon the material's properties, depending upon the material's melting point, depending upon the material's phase transition, we can able to play from one place to another place, and we can able to increase or decrease the translation speed. And finally, you can see these are all the designs our own made, and this is the top one white color you are seeing. For in order to arrest the temperature loss, we put some thermal wool bottom as well as in the top. So it is the simplest setup, and it is indigenously developed. It is not necessary to procure from other nations. And we made our own transparent furnace. And these two things, we played a very interesting role. So as a researcher, I have to know that. So for example, I can able to procure the furnace from the outside agencies. But in case if I am finding some fault, then I have to depend the engineers when he will come and then when he will rectify. In case if I am making my own setup, I can able to do repairing. I can able to rectify the problems. That is the greatest advantage. Our students, along with me, we used to make our own furnaces. So these are all the resistive furnace, and it was wounded above the quartz tube, and we can able to make it a proper distance in order to make the proper temperature profiles. Then after that, you can able to translate your ampule from top to bottom. You can able to see inside different varieties of ampules, and then we have used, because each and every ampule, why we are changing the design in order to encourage the single nucleations. Temperature profile, yes, each and every material we have to study the temperature profile of the furnace, because some material are melting point is more than 300, some material melting point is more than 250. So that ranges we have to justify, or the ranges we have to find out by using the temperature profiles. And again, simplest setup, don't think that what all the melt growth we are growing, it is very, very expensive. It is simplest setup. You need a small furnace, you can able to wind. You need a dimmer stat for controlling the temperature. You need temperature indicator and one small translation setup. You can able to do wonders, because why I am telling, many of the industries, even Foxconn, they are making semiconductor single crystals in India. Saint-Gobain, they are located at Bangalore. They are growing single crystals in our nation. But why not? Why we are not thinking that we can able to start some startup industries by only in the single crystal technologies? All nations, they are depending on the single crystals. Without the single crystals, we can able to say that there is no electronic industry, there is no photonic industry. Even oxide single crystals are playing an important role, and they are the pillars of modern technology. Whatever the technology it will come, even artificial intelligence, everything. But you have to make some electronic devices. Electronic devices always contains some of the integrated circuits, or some of them are having some single crystal substrates. So that is unavoidable. So you have to learn the single crystal technology to grow the very good quality single crystals. Then you can able to play a lot. Here we used to wind. So furnace design, we made it step by step. So then we used to seasoning the wire, that is the Kanthal wire. Then we have to wind it, and then we have to keep it inside the quartz two tubes. And for the arrest, or in order to avoid the temperature fluctuations, you have to properly pack it. So these things we have to do it before doing anything. Then we have to make our crucible designs. Earlier I have shown that there are varieties of crucible designs we can make it. Bottom portion bulb design, bottom portion V type, bottom portion that is called the tapered end. Many designs we can make, but our ultimate aim is to grow very good quality single crystal. Even I can able to make a V-shaped bottom. Even I can able to make the bulb size bottom. But my ultimate aim is to grow a very good quality single crystal, because my aim is to reduce the defects during the growth of single crystals. How the single crystals are having more defects in melt growth in comparison with the solution growth? Because solution growth, I am not playing with the high temperatures. In solution growth, I am playing with the room temperatures. Maximum it is going up to 30, 35. But in the melt growth, we are going for the high temperature materials more than 1200 to 1300. After melting, then again you have to come to room temperature. You can see the difference. More than 1200, 1300 degree difference. So whenever you are coming slowly to room temperature, then you can make a very good quality single crystal. If you are coming suddenly, then you can't be able to grow a very good quality single crystal. It will form as a glassy nature. Then we can call it as the not single crystal, then we have to call it as the amorphous. So everything simplest design, our own design. So everything we have to make it, and then we have to make a vacuum. Then after that, we have to connect with the dimmer stat. Then you can slowly increase the power. Then automatically in the center portion, it used to go for high temperature. In the bottom as well as in the top portions are always having less temperatures. And after that, what will happen? Sometimes whenever you are putting your crucible and you have to hang it, so that the hanging medium always you have to depend on some metallic wires. Through that metallic wires, sometimes your heat loss will happen. So what we have to do? The metallic wires, normally we use it to wind some thermal thread, that is called the thermal wool thread, in order to avoid the temperature fluctuations from the top as well as in the center portion. So these things we have to make an important note. And simplest things, translation setup, one small furnace, and then your dimmer stat, and then if it is possible, one temperature indicator. If it is there, then you can able to grow a very good quality single crystal. Even low temperature material also you can able to grow, because low temperature materials are having lot of applications. Some organic devices they are making. So its melting point is 96 degrees centigrade. You can see after the melting, you can see inside it is almost yellow color liquid form, that is in the molten state. And whenever it is going down slowly in the bottom, then we can able to find out from solidification starts. That means initially this material is in the solid form, that is in the powder. Then after getting the melting, after absorbing the heat, then it is going for the solidification, that molten form, liquid form, then solid, liquid, again it is solid. That is in the final single crystal form. After that, we can able to cut the crystal and all are in the similar direction. Then what are all the small wafers if you want, then you can able to cut into small pieces, maybe 5 mm by 5 mm or maybe 1 centimeter by 1 centimeter. You can see this is the benzimidazole single crystal. I have grown by slow evaporation solution growth. I have grown by Sankar Narayan Ramasamy method, that is unidirectional technique. But another one, the same material I have adopted for vertical bridgement technique. Now you can compare the same benzimidazole what I have shown earlier. The same benzimidazole single crystal, after the melt growth, you can see the size of the single crystal. Almost few centimeter size. You can see here, the same material, I have used 2 different ampules. You can see this is the V-shaped bottom. And in this you can able to see bulb-shaped bottom. Two different designs and 2 different types of crystal quality. Crystal quality means because whenever your material is in the molten form into a single crystal form, the nucleation formation is very, very important. So these type of bulb designs, it will encourage only one single nucleation. Then after that, you can able to see the cut and the polished single crystals of benzimidazole. The same material, you can go and then see in the online what is the cost of the small wafers. It is few $100s. We can able to make a very good quality single crystals with the cost-effective methods by using the vertical bridgement, by using your own design furnace, by using our own translation setup. Everything we can able to make, and we can able to grow a very good quality single crystals. Now, till now we have seen varieties of single crystals, varieties of crystal growth methods, but each and every method always needs some additions, always needs some new improvements. You can see the first cell phone was invented almost 3-4 decades before. The weight of the cell phone was approximately 500 grams. Now the same cell phone, lot of additions, lot of new improvements. The same cell phone now the weight is approximately 150 grams or 200 grams. So similarly, each and every sectors, each and every research sector, always new additions, new innovations, new improvements. Now you can see we can grow the single crystal of same benzimidazole with a double wall. Here you can able to see the one small one, that is single wall, and the same material we can able to grow by double wall. What is the difference between these two? In the single wall, what will happen? It will absorb the temperature directly. It will give it to the material or molten form, or if it is in the solidification form. Thermal shock is unavoidable. This is also one of the main reasons for your crystals are getting more defects. But another design you can able to see, this is double wall ampules. What will happen? Because the outer wall is having contact with the temperature profiles. Even outside wall is getting temperature fluctuations, it will not affect your inside wall. Inside wall is having your grown single crystal. So these type of new additions you can find out, and you can able to grow a very good quality single crystal. You can able to minimize the defects. So that is the beauty of this. Thermoelectric materials also we started working on that. I hope everyone knows about our Indian geographical condition from Kashmir to Kanyakumari, right? And still in the southern part of India, one city was there that is called Pumbuhar. Another name was Kaveri Pumbattinam. Now it is still inside the sea. Even the old Mahabalipuram, it is still inside the sea, because glaciers are melting, and we are talking about the our global warming, many things. Global warming, it is having n number of reasons. Anyway, we are all Homo sapiens. We are depending on the new technologies. Because of the new technologies, some of the side effects are unavoidable. So what we have to do? See, for example, simplest example I am telling you, in our air conditioners in our house, whenever we are having air conditioners, whenever we are switching on the air conditioners, if you go and then stand in front of the air conditioners, yes, I am feeling very chill. But at the same time, if you go and then stand in backside of the air conditioners, lot of heat, it is generating from your air conditioners, it is going waste. So these air conditioners, it is generating lot of waste heat energy, and it is pumping to our environment. This waste heat energy, what will happen? Slowly. This is also one of the reasons, global warming. You can imagine for example, like you can take the city of Bhopal. At least few lakhs of air conditioner as well as the refrigerator they are using. You can calculate the whole country, at least a few crores, few tens of crores of air conditioners and then refrigerators they are using. All are working at least for 8 to 10 hours. 8 to 10 hours, it is pumping the waste heat energy into our environment. Where the heat is going? All the heat is going to our Mother Earth. And it is also one of the major reasons. Then, as a researcher, as a responsible citizen, so we have to find out some new technologies. So that waste heat energy, how to convert into useful electrical energy. That's what the concept is, thermoelectric materials. We started working on thermoelectric materials, and then varieties of materials we started working, mainly for the figure of merit. But we used to talk about the nonlinear optical materials, nonlinear optical efficiency. Particularly for the thermoelectric materials, we used to talk about the figure of merit, that is called the ZT. So we used to grow variety of single crystals of bismuth telluride and then bismuth selenide single crystals. So whenever the technology is growing, whenever the citizens' demands are increasing, then we have to go for the new technology, new innovations, new devices. At the same time, we have to safeguard our environment. In case if we are not doing this, only we are using the sophisticated gadgets, what will happen? Now we are saying that our Indian geographical condition is from Kashmir to Kanyakumari. Maybe after few thousand or maybe few hundred years later, they used to say that once upon a time, Indian geographical condition was Kashmir to Kanyakumari. The present geographical condition is Kashmir to Madhya Pradesh. All will go inside the sea. I hope everyone knows that. In the daily newspaper, they are writing that every year, few millimeter or few centimeters slowly it is increasing. After a decade, at least a few centimeter rise will replace few crores of general citizens all over the world. So these things we have to keep in mind. And thermoelectric materials also we started working. You can see the small building, how many ACs they are using. And even the thermal plants, waste heat energy. So we started working for the thermoelectric single crystals by melt growth, that is particularly by the vertical bridgement technique. And here we have used the different varieties of crucibles, and these crucibles we have designed by our own, by keeping that some of the new nucleations in order to encourage the nucleations. Everything we made our own. Before that, we have studied its temperature profile throughout the furnace. And then because why we have to study the temperature profile or the changing the crucible designs, we have to, our main aim is, our main motive is to grow defect-free single crystals. Bismuth telluride, bismuth selenide, and then molybdenum disilicide, like that varieties of thermoelectric single crystals we have grown. And always we have to remember that the first attempt always, it may not be the success. So the crystal growers needs patience. First attempt may be failure, second attempt may be failure, third attempt may be failure. Maybe your 10th attempt may be the success. So you need patience. So nothing is impossible in our life. So that's what I used to say to all crystal growers. Impossible itself, if you put a small apostrophe, impossible becomes I am possible. So these are all our own designs. Some of them are, yes, we procured, and some of the furnaces we made our own depending upon our requirement, depending upon the materials properties. Then we have started growing varieties of single crystals. You can see some of the materials are not having the very good quality. Even from that failure experiment, we have learned many things. How to avoid the temperature fluctuations, how to change the temperature profile, how to change the temperature gradient during the growth, how to avoid the fluctuations, how to avoid the this translation setup vibrations. Everything we have learned from the failure experiments. So failure is the first step for our success, particularly for the single crystals. And then we have changed the different designs of the ampules. You can see bulb size bottom, and then V-shaped bottom also we have grown. And from that, we have studied its properties. What is the property of the single crystals we have grown? Whether that is really useful, or really it is having excellent properties, or what are all the defects inside. So if the defects are more, how to avoid. So many things we have come to know, because anyway, few of the slides only I have taken. And these are all the very good quality single crystals we have grown by vertical abridgment technique. You can able to see, we can able to slice small pieces also. And some of the experimental characterization techniques we have carried out. And you can see before the growth, yes, we have taken some of the ampules, and then some of the wafers also we have taken. And this is the another one. This is called the molybdenum magnesium silicide single crystal. And through this, yes, we have grown double wall ampule. And from this, we have taken varieties of materials, and then varieties of experiments, and the number of experiments we have carried out. And finally, we have taken very good quality single crystals. You can see. Before that, we have to find out the experimental profile details. After that, only we can able to grow a very good quality single crystal, because through profile, you will come to know many of the if and buts, many of the negative points, many of the positive points. If you know precisely your temperature profile of the furnace, then you can able to play. Now you can see this profile. It is starting from the room temperature, and it is going for a very high temperature, and again it is coming to room temperature. So that's what I used to say, that crystal growth is an art, because you are going to very high temperature, and again you are coming to room temperature. So that the temperature difference you have to control very precisely. Then only you can able to grow a very good quality single crystal. And you can see here, so some of the experiments, initial experiments, yes, failure. After that, yes, we have changed some of the temperature profile part, and finally successfully we have grown the magnesium disilicide single crystal, bismuth selenide single crystal. You can see some of the crystals we have grown. And that's what I used to say, that in the experimental part, failures are normal. So through failure we have to learn. Through failure we have to change our strategy, change our designs, change our research methodology. Then after that, definitely you can able to grow a very good quality single crystals. You can see graphite crucibles we have taken, and then we studied what is the failure, what is the content. If it is a success, what is the content. So through various characteristic analysis we have grown. And then HBN crucible also we have taken, because outside crucible is quartz, and inside HBN crucible, that is hexagonal boron nitride crucible, that is called the white graphite. I am audible? Hello?
Yes, sir. Yes, sir. You are audible, sir. Clear.
Yeah, one important call is coming. Just 1 minute, sir.
Okay, okay, sir. From audience, I request Tangaraja sir to please carefully handle your mic, because 2 times it was disturbed the speaker.
Yeah, it is visible, sir.
Yes, sir, you are visible, sir. You can proceed.
Yeah.
Okay,
See,
sir.
now, another material we have taken, that is a cadmium zinc telluride. Cadmium telluride, it is one of the best materials for detector applications we have taken. And what we have done, we have grown the single crystal in the laboratory conditions. What are all the laboratory conditions? You are having temperature profile, that is common, but you are having gravitational force. Gravitational force, indirectly, sometimes it may influence the formation of the defects. What we have done, this one crystal we have taken, that is called the cadmium zinc telluride, we have grown in the laboratory scale. The same material we have grown in the zero gravitational field, that is in the space. So we compared the crystal quality. What is the quality of the crystal we have grown in the laboratory scale, that is in our earth? What is the quality of the single crystal? It was already formed through the same Bridgman technique in the space. So what are all the differences? So we have written an excellent article. You can go and then you can find out cadmium zinc telluride by putting our name. And then in addition to that, cadmium zinc telluride, see, normally it is having very high temperatures. See, the growing of a cadmium zinc telluride is the challenging task. So approximately we have used more than 13 to 14 different thermocouples for controlling the precise temperature. Then after that, we have loaded our ampule, and then our ampule is going from the top to bottom. Here you can able to see the furnace, we can able to rock it clockwise as well as the anti-clockwise. Why? Because cadmium zinc telluride during the melt, if you properly, with proper rotation of 45-degree clockwise as well as the anti-clockwise, if you rotate during the molten state, it will mix it properly. That is cadmium, zinc, and then telluride. And in case without the rocking or without the changing of your furnace, so in case if you grow directly, sometimes the mixture may not be proper. Sometimes you may get a very high cadmium content. Sometimes you may be getting less cadmium content. So these are all the things. So this one also we have learned from our failure experiment, and then we have modified the furnace, and then we have grown very good quality single crystals of cadmium zinc telluride. So this is the mission, that is Photon M3. Through this only, our members, collaborators, they have grown the cadmium zinc telluride in the zero gravitational condition, and the same crystal we have grown in our laboratory. So Russian team, and then we have compared the crystal quality. So that is, it came in a very, very fantastic article, and it is till date. It was one of the highest downloaded articles in the optoelectronic materials, JOM, Journal of Optoelectronic Materials. You can go and then find out. And a very nice patent also we have filed by using the vertical gradient freezing system. Till now we have seen vertical Bridgman system or Zuchralski system. Your furnace is stationary, and your ampule, that is the container, it is coming from the top to bottom or bottom to top. So through the Zuchralski. But here vertical gradient furnace mean your furnace is stationary. Your ampule is also stationary. We are not going to change anything. If we are changing, what will happen? In the normal vertical Bridgman technique, earlier I told, translation system, you are coming in the speed of 1 mm per hour or 2 mm per hour or 0.5 mm per hour. What will happen? The translation setup, sometimes it will create vibrations. That is unavoidable. So that micro vibrations will generate micro defects inside the crystal. Instead of that, I need a stationary ampule, I need a stationary furnace. Then we made the vertical gradient freezing system. What will happen inside? Here we used to set the programs, and only the profiles, it will change from one part of the ampule to another part of the ampule. That's what we have wounded up approximately 5 different furnaces, and we maintained for 5 different zones. And here, definitely you will get a very good quality single crystal. The main reason is you are not changing your ampule. You are not translating your ampule from one place to another place. And at the same time, your furnace is also stationary. Only you are working or changing the temperature profiles. So that is one of the best methods I found. And then we have grown very good quality single crystal. And the same thing we have filed a patent also. And harvested cadmium zinc telluride ingot. Sometimes what will happen, in case if you are not going for the proper dynamic vacuum, sometimes it will explode also. So we have to be very careful. You can see bulged portion of the ampules. and we have grown, and then we have learned some of the failures, and then through that we have rectified the furnace, and then rectified the designs, rectified the temperature profiles, and finally we have grown very good quality single crystals. And this is the another design. So normally whenever we are translating one ampule from top to bottom, so only we are hanging the through wire, and then it is coming from top to bottom. And whenever it is having some support in the bottom, what will happen? The support also will absorb some temperature. So whenever it is coming to the end of the bottom, what will happen? The already it is, what all the temperature it has taken during the high temperature, it will slowly release even if it is coming to the golden zone, or whenever it is coming to the cooler zone. So the ampule support, it will slowly release the temperature to the crystal, and it will it acts like a self annealing. So definitely your crystal quality will be really extraordinary. These things also we have taken. You can see double wall ampules, and by using our own design of our transparent furnace, we have grown varieties of crystals. Not only that, we have adopted the Czochralski technique also. Czochralski technique, we have used the RF furnace, radio frequency furnace, and above that we have made one resistive heating small element, because after the growth we have to keep it for some time in order to come to room temperature slowly, because the melting temperature is approximately 1233 degrees centigrade. So whenever you are working for the very high temperature, what will happen? Sometimes you are coming to room temperature, the cracks will happen, or the cracks indirectly it will generate lot of defects. So for avoiding that, we made our own, only RF furnace we have taken, and resistive heating we made it as by our own, and we have grown varieties of single crystals. And always remember, these single crystals are having different applications. These single crystals are having different varieties. So varieties of single crystals we have grown by varieties of methods. One is slow evaporation solution growth, another one is vertical bridgement technique, third one you are seeing, that is a simple table salt, NaCl, sodium chloride single crystal, we have grown. Whenever it is in the single crystal form, you can able to see the applications, that is the IR window applications. We can able to grow, and then we can able to make the devices from the IR window applications. Bismuth germanium oxide, it is one of the best detector single crystals. Lithium niobate with the different dopants. Not only that, alkali halide single crystals. These are all the single crystals we have grown by Czochralski technique, very high temperature. You can see Czochralski technique, one small disadvantage is you need a seed crystal of the similar orientation. If you are having, then definitely you can able to grow a very good quality single crystals. And the last one you are seeing, that is the potassium dihydrogen phosphate single crystal. You can see the quality of the single crystal. That is grown by slow evaporation solution growth. And as a researcher, my responsibility is I have to make the simple way to grow the very good quality single crystal. I have to report that how I have reduced the defects to the international community. So all my PhD students, they worked very hard, and we made our own designs, and continuously we used to publish very good quality papers. At least each and every paper you can go and then see in the literature, at least some new concept we used to propose. Effect of ampule support, how the ampule support is given or it is induced for the growth of very good quality single crystal, particularly for the organic materials. Even inorganic materials, some reports are there, but organic materials controlling the temperature is very tedious. So this one also we have already reported. And then enhancement of thermoelectric figure of merit, because normally figure of merit, that is ZT, particularly for the thermoelectric single crystals, it will vary. If it is in the perfect single crystal, definitely your value drastically increases. So by changing the designs, by changing the ampule designs, so we made the figure of merit in the extraordinary level, bismuth, not in a very high level, at least already reported, and then few, times it is better. Bismuth selenide and then bismuth telluride single crystals we have grown. And not only that, how the nucleation is forming, what is the size of the nuclei. So by doing the theoretical analysis, we have reported, that is called the sulfamic acid single crystals. Double wall, how the double wall, single wall, what is the variation, how the defects we can able to control. So this one also we have studied in a thorough way. And after that, you can see different materials, different techniques, and each and every technique, it is having its own advantage, it is having its own disadvantage. So these things we have compared with the different techniques, and we have compared the characterization part also, and then we reported in a good journal. And then comparative study also we have done for the slow evaporation as well as the Sankarnarayan Ramasamy method, as well as the unidirectional technique also, and the VBT also we have grown. And in the L-alanine, normally as a single crystal grower, we are having varieties of techniques. Particularly for the slow evaporation solution growth, we are having slow evaporation or slow cooling. There is one more technique is there that is called the seed hanging technique. The seed hanging technique, L-alanine, yes, we have grown, and then whenever it is inside the seed, it is having some thread. How the thread is influencing the other part of the single crystals, how the defects are increasing, those analysis also we have done. And then other material for the nonlinear optical applications, and then how the crystal growth, and then how the terahertz materials, how we can able to improve by controlling its different temperature, conditions, how we can able to grow a very good quality single crystals. And then another material that is called the L-threonium, and then nimhydrine, we have grown by slow evaporation as well as the unidirectional technique, and we compared the techniques. Nucleation kinetics already I have shown. And then L-proline cadmium chloride, because as a crystal grower, my aim is to find out the potential nonlinear optical material. Not only that, at the same time I can able to grow a very good quality single crystal. Then only I can able to propose for the particular applications. So these things also we have series of papers, series of good reports we are making. And then structural optical thermal properties of co-dopant zirconium, and then iron doped, co-doped congruent lithium niobate single crystals we have grown. Sulfamic acid single crystals, many number of crystals, all are having very good optical behavior. Optoelectronic materials directly we can make it. Not only that, each and every paper, each and every report we have given some new novel concept, how to grow, how to design, how to make your own ampule, how to make your own furnace setup. Even the instrument journal also we have reported a few of the papers. Instrument Society of India. So many materials, an in-depth study for the growth of 4-amino benzoates, a potential candidate for the electro-optical applications. And then some of the chiral compounds also we started working for that. Potassium niobate, lithium niobate, potassium niobate with the different dopants, how it is increasing the piezoelectric coefficient. This one also we have studied. And then comparative analysis, benzimidazole single crystal we have grown by Sankarnarayan Ramasamy method. So almost 8 PhD students, they have completed each and every student, some novelty they have contributed to our research work, that is in the area of single crystals. And some applications, ACSIR, Academy of Scientific and Innovative Research, at the end of the PhD, they have to propose some program that is called the CSIR 800, that is 800 million poverty people in India. What all the research outcome is coming from your research, you have to propose some models. Some of these students, they have proposed some thermoelectric models. Some of the students, they have proposed the piezoelectric single crystal, that is piezoelectric based speed breakers. So many, even the blind person stick based on the piezoelectric concept. So each and every student, they contributed for the development of new technology, development of new innovations, development of the new devices from their own research. So this is not my own work. So anyway, all my PhD students, they have rigorously, tirelessly, they are working very hard, and then they made the new informations, and then new concept to be proposed for the new concepts to be proposed to the scientific communities. So I will not take much of your time. And one more information I want to say that, because why I have focused for this optoelectric material, particularly I have taken the single crystal growth. Earlier I have mentioned that in India, we are not having any crystal growth industry by our own Indians. Even few of the crystal growth industries, even we are purchasing the silicon single crystals from abroad. Even we are taking some detector single crystals from abroad. Even if you go and then discuss some of the IIT professors, they are saying that, yes, these single crystal wafers, these single crystal substrates I am taking from abroad by paying few $100,000. Why not? We can make our own. We can make our own technology. We can make our own startup industries. We can make our own India, the new India, the vibrant India. So that's what I used to say that. So it is not only from local. So we have to always vocal for our local also. So this is my main message to convey to the youngsters and the audience. So if you are having any questions, yes, we can go for some discussions.
Thank you very much.
Thank you very
Right.
much.
I thank all the participants, especially Vijayan sir. It was very great time with you, and always your talk is enthusiastic and energetic. We got more energy from you today. Thank you very much,
Thank you,
and
sir.
I thank you, sir. And I thank our all participants. And it's closing time for day 2. As usual, you join the session by tomorrow. The tomorrow sessions will start by 6 o'clock. Thank you, one and all. Thank you.